Hello guys, good morning to everyone. So this is the next session on Pelton Wheel. So in the last session we have seen the derivation regarding the Pelton Wheel, the maximum hydraulic efficiency, condition for maximum hydraulic efficiency, all those things, effect of friction, all those things we have seen in the last session. So in this today's session I'll be going to talk about some efficiencies and related to some problems on it. Okay, so today's class we will go like this. So first, defining of some efficiency, defining efficiencies. Next will be the case of what it is. Design consideration for Pelton wheel. For Pelton wheel. Design consideration for Pelton wheel. Then the third will be problems, simple problems. So in this today's session, I'll be taking the help of the some problems from directly from textbook Turbo Machinery, BK Venkana. I'll be taking the problems and some definitions all from the textbook by Turbo Machinery by BK Venkana. Okay, so this is the starting of it. The first one will be the hydraulic efficiency, mechanical efficiency, volumetric efficiency, and overall efficiency. The first is what? Hydraulic efficiency. Here we already say that what is efficiency? Efficiency is nothing but output by input. Generally what will be the efficiency means? The efficiency will be output by input. So what is the output here? Power developed by the runner to the power supplied to the bucket at inlet. So that will be given by rho A V1 VW1 plus VW2 into U. This is what the power which we have already derived it. Rho A V1 VW1 plus VW2 into U. This derivation is already been done. So that power, so the derived power obtained, that I'm substituting over here, and the divided by the kinetic energy that I'm going to divide over here. So this is what rho A V1 VW1 plus VW2 into U half m V1 square. So this is what is going to happen here. So if we divide it, if we see here, this m can be written as rho A V1, rho A V1, rho A V1 goes off. So the remaining thing is 2U1 VW1 plus VW2 by V1 square. Okay, or we can also write this as rho AV1 water power, that is rho Q GH. These are the two things you should remember here. The hydraulic efficiency is given by this formula or by this formula. Okay, so this is what the hydraulic efficiency is. So the next is the mechanical efficiency. It is defined as power at the shaft of the turbine to the power developed by the runner. So this is what the mechanical efficiency. And the volumetric efficiency is volume of water actually striking the runner by the volume of water leaving the nozzle. So this is the volumetric efficiency. Overall efficiency is power developed at the shaft of the runner to the power at the inlet of the runner. So if we divide that, we get theta m into neta h, okay, or neta m into neta h into neta v. So here I want to give you a basic definition of it. Let us say I will divide this as, so let us say this is, I'm using the block diagram here. This is the runner, this is the shaft. Okay, so now this is the inlet water, this is the power by runner it is, and this is power by shaft. Okay, now if I divide, what is efficiency? It is output by input, correct? This efficiency is output by input. If I divide this by this, if I divide power, shaft power by runner power, which efficiency I will get? I will get this mechanical efficiency. Shaft power here, this one. If I divide this by this, I will get shaft power by this. Now, if I divide this by diff, that is power by runner power by water power. If I divide that, I will get hydraulic efficiency. Correct? So what is overall efficiency? This divided by this. If I do the division of power developed at the shaft of the runner to the inlet power, if I divide this by this, then I will get the total overall efficiency. That is shaft power by power, water power. Now if I divide this by runner power, both side, runner power by runner power. So what this shaft power by runner power gives you? The shaft power by runner power gives you a mechanical efficiency, and runner power by water power gives you hydraulic efficiency. Therefore, the overall efficiency is mechanical efficiency into hydraulic efficiency. Yes. Now, if we consider that volume also affects the volume, how much of volume is living out, how much of volume is living in, if we consider that also into consideration, then we can use the term volumetric efficiency also to define the overall efficiency. Okay. By this way, I think it becomes easy for you to remember the things. So what I will write the formula also. What is the power of shaft is given by shaft power. The runner power is given by rho A V1 VW1 plus VW2 into U, and the inlet water power is given by half V1 square, half m V1 square, or we can write it as half rho A V1 into V1 square. Yes, right? Correct here. Rho A V1, sorry, half m rho A V1 into V1 square. Correct. That I can write it over here. So if you divide one by other, the one by other, you will get these efficiencies. Hope that I have conveyed these efficiencies well now. Okay, now coming to the important design parameters for Pelton wheel. Remember these are very important here. So the V1 jet velocity is given by CV root 2GH. H is net or effective head. CV should be 0.96 to 0.98. This is the design configuration for Pelton wheel. Next, U is given by mean velocity. So U is 5 root 2GH pi dn by 60. Okay. So that is what here, and the jet deflection angle is 165 degree, which is the thing here. What it is 165 degree, which we see here. Deflection angle here we have seen here 165 degree. So jet deflection angle is also 165 degree here. Okay. So then comes the Z d by 2d plus 15. Z is what? Number of buckets. Number of buckets is given by 15 plus 0.5 m. And cross-sectional area of the jet is given by pi by 4 d square. Discharge from the nozzle width. These are all the design consideration which you have to remember here. Okay. So if you remember that, we can use those in the problems. Okay. I will start with some of the small problems here. Okay. A Pelton wheel develops 5800 kilowatt under a net head of 180 meter at a speed of 195 rpm. Find the discharge through the turbine, the wheel diameter, the number of jets required, and the specific speed. Use the following assumption. Overall efficiency 86%, d by d is 12, and phi is 0.45, and CV is equal to 0.985. Okay, these are the things which is been given in a question. So power developed is how much here? So this is what power developed. A Pelton wheel develops 5800 kilowatt of power. So whenever we say that a Pelton wheel develops, we have to consider this as the runner power. 5800 kilowatt is a runner power. This is the head at which it is working. Speed n 195 rpm. Find the discharge to the turbine, the wheel diameter, the number of jets required, and specific speed. This I will come later. What is the specific speed? Use the following assumption. Overall efficiency d by d, phi is equal to 0.45 and CV equal to 0.985. They had given this jet ratio. I think this is this is what jet ratio is. Jet ratio m. Jet ratio is, what is jet ratio? diameter of the wheel by the jet diameter. Diameter of wheel by jet diameter. That is what jet ratio is. So these are things which has been given here. So how to begin with the problem? Overall efficiency is this, jet ratio 12, CV 5. Okay. Commonly, if it is not given, the jet ratio will always commonly it will be equal to 12 in common. If they have not given, then we can consider it has to be 12. Okay. So the wheel of the diameter of the wheel D is given by V1 equal to CV root 2GH. Correct. So if we consider this is already a design consideration here, so we'll start with that only, v1 equal to cv root 2 gh. So they had given here cv as what, 0.985. so this you substitute here, h you substitute, j you substitute, we'll get the v1. Same way u is also been given here. What is u given by? 5 root 2 gh or pi dn by 60. So you can use 5 root 2 gh, just substitute here, you will get the u also. Now using u, what is u? Pi dn by 60. This also I have already explained how why it is pi dn by 60. Using this, you can consider what is the diameter, wheel diameter, you will get it here. Now using that wheel diameter, substitute it in the jet ratio. It is given by d by d equal to 12. So the jet ratio d is small d is equal to d by 12. That is given by 0.218 meter. Okay, so the number of jets. So how to find the number of jets? So consider overall efficiency. Overall efficiency is shaft power by kinetic energy, or the power at the water power. Shaft power, I'll just write it as shaft power by water power, or kinetic energy of water power. So if I substitute over here shaft power by rho q g h, you will get the discharge as 3.82 meter cube per second. But what is discharge is equal to number of jets into 1 number of jets into area of, or the discharge of one jet, pi by 4 d square v1. If we substitute that, we will get the number of jets here. Always remember here what is this explanation I am giving it over here. So let us say this is the one nozzle through which the jet is emerging out. Okay, and this jet hits the Pelton wheel. Okay, so this is one jet which is hitting the Pelton wheel. So there will be number of jets which will be hitting this Pelton wheel. Okay, there will be number of jets, one jet. So the total discharge Q is equal to the n number of jets into discharge of each jet. Yes, so let us say if there are two jets here, then the total discharge will be equal to Q equal to 2 into discharge of each jet. So what is the discharge formula is given by? Q is equal to, discharge is given by area into velocity. Discharge is given by area into velocity. Correct. So now what is area given by? Discharge, sorry, small discharge Q I'll take, pi by 4 dj square into V1. Correct, because dj is the area of this small jet, dj square into V1. So capital Q is given by number of jets into discharge of single jet. So Q equal to total discharge is equal to number of jet into discharge of single jet. So that is given by what? Pi by 4. So number of jets is equal to Q, the total discharge. The total discharge you have found it using this overall efficiency formula, that 3.82 whole divided by discharge of single jet, that is pi by 4 dj also you know, v1 also you know. Substitute it, you will get it has 1.974. So number of jets cannot be a decimal, so it has to be a whole number. Round it off to the nearest number, so that becomes the number of jets is equal to 2. So this is the thing which we are going to see here. This specific feed you need not to worry about it. It is just the formula n root p divided by h raised to 5 by 4, which is not required for you. Okay, have you understood this? I think this is little it's very simple problem, it's not so complicated. I'll just give 1-2 minutes again a revision of this. So go through this problem once, then we can further go again. So next is this. So how we are beginning the problems. This is by the our design concept considerations. 100% here you have to go through this design consideration. There is no escapism from it. You should know this design consideration. I will just write it here. It's simple here. Design considerations are simple. V1 equal to CV root 2GH. This formula you should know. U equal to phi root 2GH. Sorry, phi by 2GH, right? Phi by root 2GH, correct. No, phi root 2GH. Phi root 2GH, which is also equal to pi dn by 60. Okay, here you should know that CV should be equal to 0.95 to 0.98. I guess, just a second. Correct, 0.96 to 0.98. That's fine. Sometimes they will give, sometimes they might not give. And here, phi is always equal to, phi value is here 0.43 to 0.46. 46. Okay, so this is the second formula which you should know here. Then coming to the number jet ratio, jet ratio is given by diameter, capital diameter by the small diameter, where capital diameter is wheel diameter or turbine diameter by jet diameter. Okay, so next coming to number of buckets. So this is the here two things here. Don't get confused between the number of buckets and the number of jets. So for that reason, I'm just making it clear. Number of buckets is Z. That is given by what? D by 15 plus 0.5 m. Just remember this, 15 plus 0.5 m. If we consider D by D as 12, almost all times it will be 12. If I consider D by D as 12, so we can say that it is sorry, if 15 plus 0.5 d by d is almost equal to 12, almost times. Okay, so then coming to the number of jets. So number of jets formula you remember here. The number of jets is total discharge by discharge of single jet. Okay, total discharge by discharge of one jet. So that gives you the number of jets here. Okay, so next coming to width, length, that we can go through later. But these formulas must remember. There is no escapism from these formulas. Okay, so these are some of the things here. Okay, so let's see for the next then. Okay, a Pelton wheel has a water supply rate of 5 meter cube per second at a head of 256 meter and runs at 500 rpm. Assuming a turbine efficiency of 0.85 or coefficient velocity for nozzle as 0.985, speed ratio, you just note it down what all the things here meanwhile. Okay, so what it is, a Pelton wheel has a water supply rate, this is what total discharge, 5 meter cube per second at the head of 256 meter, this is head. Okay, then runs at 500 rpm. Meanwhile, you just make a habit of writing it, whatever you write it. Okay, assuming a turbine efficiency is always called as overall efficiency, 0.85. If this turbine efficiency means overall efficiency, a coefficient of velocity for nozzle as 0.985. Coefficient of velocity is 0.985. Okay, speed ratio is 0.46. This is speed ratio, 0.46. Okay, then calculate power output specific, all that we'll see. Okay, so these are the things which they had given here. Now first V1, start with the same design consideration, CV root 2GH. CV they had given, H they had given, G you know, find it. So same way, U equal to phi root 2GH. Phi is given, H is given, find phi U. Okay, now coming to U is also equal to pi dn by 60. So find the diameter. Find the diameter. Okay, now what is overall efficiency? Overall efficiency will be what? Shaft power or the runner power, shaft power by what? Rho QGH. Now you need the shaft power here. So shaft power is given by what? Power delivered will be given by rho QGH into efficiency. So substitute that, you will get this. Again, this is not required for us. So this is what the 1067 73.3 kilowatt. This we will get it from the what power. The power is this much. So using that, so we already found the wheel diameter. Now jet diameter. So jet diameter is what? Number of jets you have to find. Number of jets is equal to total discharge by discharge of single jet. Okay, so if we consider that, here there is one more formula which they have obtained here, considering specific speed for n jets by 30. So this assumption, I don't think so it is referred in your syllabus. Specific speed for one jet, just consider this as a reference as of now. I will come back to this later. Reference for single jet it will be that much, so or it will be 2. So other than that, if it is not given, then you can consider the number of jets is equal to 1. If it is not given, if any case it is not given, the data is missing, then you can consider for single jet and you can do the calculations. There is no doubt about it. Okay, so if you consider single jet, and you can do the derivations. Now you check this one. So pi by 4 d square into what it is, pi by 4 d square into v1 is equal to total discharge. If we do that, you will get a single d square. What is the single d? You will get it. Okay, so that is the next thing here. So number of cups, this formula, you just substitute cup dimension. This formula is also available here, 2.8d. Just remember this, 2.8d, 2.4d, 2.6d. Okay, this is also a design consideration. So this is what the using the design considerations here. Since you have this type of problem also here, this problem also I'll be discussing here over here. So because you have already derived the problems using velocity triangles, this problem might come for you. So for that reason, see here the 3 jet Pelton wheel. So they had given here the number of jets as 3 is required to generate 10,000 kilowatt under a net head of 400 meter. So what it is then, to generate 10,000 kilowatt, shaft power is what? 10,000 kilowatt. The blade angle at outlet is 15 degree. At outlet blade angle 15 degree. This is very important. You should, by looking at the question, you should understand what is the data. Then only you can solve the problem. So 400 meter here. Beta is equal to 15 degree. H is equal to 400 meter. So the blade angle at outlet is 15 degree, and the reduction in the relative velocity while passing over the blade is 5%. So this is K. K is 5% is reduction. So the available is what then? 0.95. So 0.95 still available. So 900 minus 5%, that is 95%. 95 if you express it, you will get 0.95. If the overall efficiency of the wheel is 80%, CV is 0.98 and speed ratio is 0.46. Calculate the total flow in meter cube per second, diameter of the jet, force exerted by jet on the buckets. So these are the things here. So the number of jets, they had given it as 3. All those things I have noted it down. So now, so first start with V1. CV root 2GH. Substitute the things here. You will get same U, 5 root 2GH. Substitute the things. Now comes the concept of velocity triangles here. Always remember to draw the velocity triangle. Sorry. I'm just drawing this velocity triangle. This is your V1 equal to VW1. This is U1. This is VR1. So this will be, I think, beta 1, alpha 1. Just I will refer it. But that should not get confused. Beta 2, alpha 2. So this is beta 2, alpha 2, VR2, V2, Vf2, okay, U2, Vw2. So these are the things which is the velocity triangle here. So using this velocity triangle only we can do all these things. So VR2, this we know, K is equal to what? VR2 by VR1. Yes. So how can you find VR1 here? So VR1 is equal to V1 minus U1. If you substitute V1 minus V1 also you know, U also you know. If you substitute that, you will get VR1. So substitute in that. So what is VR2? K into VR1. So that also you'll get VR2. Now, how can you find VR2, VW2 here? VW2 is VR2 cos beta 2 minus U2. This also I have explained while doing the derivation. VR2 cos beta 2 minus U, or U1 equal to U2 here. So VR2 minus cos beta 2 minus U. VR2 cos beta 2 minus U. So substitute that, we will get the VW2. Now using this VW2, we can substitute that in the power, VW1 plus VW2 there. So our overall efficiency is this much. Using that, you can find the Q. Okay. So the jet diameter is given by what? Q by Nj. So that will give the small q. So small q is equal to 1.026 pi by 4 d square v1. We will get the small t. So force in x direction, rho q vw1 plus vw2. Here we need the vw1 and vw2. Therefore we have found the vw1 and vw2 over here. So substituting that, we will get the force in x direction. So this is what the one more type of problem here. A few more type of problem will be given as an assignment for you. Just try to do it. If you get, it's well and good. Otherwise, I will take one more class to explain those assignments as well. Okay. So just go through this problem again. So that will be the end of the today's class. Okay. Okay, guys. Then fine then. So we'll meet you in the next class then. Till then, bye.